he will be speaking about the causality without the use of controlled experiments in e-commerce. And before we start, I would like to invite everybody to ask questions in the live chat on YouTube. All these questions will be addressed after the talk in the Q&A session. So, Emir, welcome.
Okay, hello everybody. So I'm Emir. This is the talk towards causality without controlled experiments. I guess let's start with a little bit about me or reasons to listen. So academically, I guess maths and applied maths have been my bag mostly. Commercially, about 15 years working as either a software engineer or a data scientist in London. Mostly with startups and scale-ups, mostly in SaaS, so lots of project experience. And at the moment, I am consulting for CGI in Malmö as a senior data scientist. So CGI is a really big consultancy company and a really great place to be if you like diversity of projects. Because in 1 year, you could be doing... Yes.
Maybe you would like to make the slides full screen.
Oh, if you prefer. I actually like them like this.
Yeah, it might be better for those who watch the slides.
Yes, slideshow. Start from first slide. Where was I? Yes, so CGI, large company.
I think the slides are in the separate window now.
Oh, good times. Okay. Okay.
No problem.
You get to watch me struggle with the slides, in which case, so I think I have to maybe
you can share the other screen or the other application now, or
yeah, just trying to do that. Let's see if it comes up or not. Yes, looks like it has. Slavic, are we winning?
Yes, great. Thanks, and sorry for interrupting.
No problems. Where was I? So yeah, CGI, large consultancy company, lots of projects. That's what I do at the moment, based in Malmö, Sweden. Good place to be if you like diversity of projects. Just try and catch up on the time. So we'll be talking about causality primarily. I have to start by telling you what that is and how it relates to experimentation. And then we'll sort of snowball from there. Okay. Causality is philosophically complicated. What it means is not obvious. But a popular kind of practical definition is kind of a way of defining causality in terms of counterfactuals. And loosely put, how that's often phrased is A causally depends on B if A happening means B happening and not A happening means not B happening. But really, it kind of means if A didn't happen, B would not have happened. And if A does happen, B would happen. So this would not have happened aspect of it is a little bit weird because we don't have access to that in the world. You know, things either happen for us or they don't happen. And we have no way of knowing what would have happened had something been done differently. So to try and sort of usefully deal with causality in the sort of experimental setting, we make a sort of key assumption. So first of all, we assume that we can get a bunch of things that are completely identical to each other. And then we say, okay, well, I'm going to try and do some different things to those things. And because they're otherwise completely identical to each other, the differences in consequences must be as a result of the differences in treatment. So the sort of working assumption there is called ceteris paribus, or as you might do it in English, but maybe ceteris paribus if Latin sounds anything like Italian. And it basically means all other things being equal. And it's a sort of the stable assumption for experimental designs. So to speak about a concrete design and sort of unpack this concept a little bit more, the humble A/B test. So that's just your basic A/B test, the sort that many people know about. You split some group 50-50 into two subgroups, and you make sure the sample is big enough to represent the whole population that you're trying to reason about. and you make sure your splitting happens at random. And the random part here is super important, because that's what makes ceteris paribus possible. So when you randomly allocate your things between group A or group B, what you're also doing is making sure that the things being allocated have an equal chance of being affected by all of those other things that you don't care about. Now what you do is you treat group A, but you don't treat group B. And what you get as a result is a treated group, a not treated group, that are otherwise equally affected by everything else that might be happening. So when you, after the treatment, when you do some measuring on these groups, hopefully all the differences, or most of the differences that you see in your measurements, will be as a result of the difference between the groups, which is just your treatment. Hopefully that makes sense, but I have no way of knowing. Okay. So how does this all relate to e-commerce? This talk is kind of focused on e-commerce, but it need not be. This applies pretty broadly. So a really popular question is, I want to make some changes to pages. Do they improve something I care about, like engagement or conversion or the number of people that sign up or whatever? It's also really useful for testing things like layouts. And does this improve? Are more people likely to read our terms and conditions if we do this, or whatever? Also, user journeys. Do more people complete the journey if I remove this thing from the checkout process, or if I add this thing to the checkout process, and so on. And what's more, it's just very prominent amongst big organized companies with a firm presence on the web. So a fun project is to use something like Common Crawl, which is like a free web crawl, to go and see how many optimizely VWO or Google optimized JavaScript includes you can find amongst the top rated sites. And my assumption would be it's in 90% if they do retail. So very, very common. However, it's got oodles of kind of practical issues for the working data scientist. First big issue is, companies typically have a ton of historical data, and you can't do randomized control trials on historical data. Or you have something like an e-commerce experience where you have maybe lots and lots and lots of different products. And the only way you can really test whether something is true across all of them is to sort of test all of them. But then if you've got tens of thousands of products, that can quickly become prohibitive for other reasons. Lots of folks have built platforms or have a presence that just doesn't include A/B testing inside of it. And as a result, it's difficult to put in kind of as an afterthought sometimes. And as a result, people don't use it. And the final thing is, as soon as you start to get a bit clever about how you want to do your experiments online, A/B testing, you need more than A/B testing. There's lots of fancy pants things, and all of them sort of require a statistical, or most of them require a proper statistical background to analyze. The A/B test and some factor test experiments are maybe an exception to that rule, but most things require a bit of fancy footwork. So in the real world, what you tend to see in commercial data science is lots and lots of observational studies. So you're trying to do something that you probably should do with an A/B test, but without using an A/B test. And this usually starts with somebody saying, oh, this thing is happening, or it's not happening, or we need to make a decision, go and explore the data and work it out. But you haven't got ceteris paribus, no A/B tests. And your biggest problems usually end up being the question, well, how do I know? How do I know that if I'm trying to work out whether something affects something else, how do I know that these two things happened causally and that they wouldn't have happened anyway? Okay, so to give you a sort of a living example, sort of a bastardized real one from my actual life. So marketers at an online retailer push content to product pages and want to know if it made a difference to conversion rates. They've got a huge number of products, and they're very international and cover a lot of different markets. And they want to be able to have this functionality everywhere. There's many different teams affecting the same stuff. No given person knows what is happening to any given product at any given time. So about as messy as it gets. Guy does a thing to product X, and Guy wants to know did the thing make a difference to conversion. So like I said, no A/B tests. Conversion rates in products change like crazy for no apparent reason. So it's very difficult to to eyeball it and make a decision on whether it was whether it's skyrocketing because of something you did or because it's skyrocketing because it just does that quite often. Okay, so when faced with this sort of question, I'm going to do a bit of a hat tip to how this is mostly done, and then kind of go off on a tangent because it's more interesting. So one way to approach this sort of problem is that you come up with a predictive model that tries to predict what the conversion rate of your product is going to be, and your predictive model has to be amazing and do a really good job of doing that. And then once a change supposedly happens, you can ask the question, what does the model think should have happened? And if the model gets it wrong, but usually gets it right, then you conclude, well, that's because something has changed, and the model no longer understands. So something systematic has happened. The model doesn't predict, therefore a change has occurred. So that's quite useful. That's quite common. The other thing is trying to do the equivalent of an A/B test. So sort of build that sort of randomized group contrast, but without randomization. So in other words, trying to build a synthetic control group. And this is a sort of established methodology where you try and match the thing that's changing to things that to other things that probably aren't changing, and compare the two to try and work out whether something really happened. Or there's the third wild card, which is something completely out of the blue, which is what I want to talk about. So here's a sort of thing you can try that I'm going to call relationship analysis. It exists in many guises, in many places, but it doesn't really have a sort of calling card or a name. And I will describe it. So products in this use case are very related to each other, especially if they are in the same category. And there's loads of reasons for that. So often products are complements for each other. You buy one and you buy the other as a complement, or they're alternatives. If you buy one, you definitely don't buy the other. Or the marketing department is pushing all of that range at the same time. Or the website is actually designed so that products are like presented together, as websites tend to be for e-commerce. And all of these things end up creating relationships between products. And what's very interesting to notice is that if you change your product, then what you're also doing is changing how it's related to all of the other products. So if product A and B are well related, and you have a way of quantifying their sort of steady state relationship as, let's say, a number, but then you change A, but you don't change B, what you'll see is that the relationship changes between A and B. So an example of that would be like adding user reviews to a product to see if that makes things better or worse. But as a result, the way that users interact with that page now changes. It starts to convert differently, and as a result, its relationship to all the other products change. An important thing here is that it may be easier to analyze the relationship between things than it is to do the other things, like build very good predictive models or engineer synthetic control groups. In my use case, it very much is, because it needs to apply to a huge number of products, and it's very difficult to do the other things well in an automatic way. This sort of approach, which I'll unpack a little bit on the next slide, has been used for stock market regime change. You have correlations between stocks. When the markets are tanking, everything tends to become extremely correlated together, and this becomes like a flag. I'm making this simpler than it needs to be, but that becomes a flag that something bad is happening. And also in like EEG, sort of like brain monitoring, what the brain does kind of is coordinated, and when the coordination changes, something in the brain has usefully changed. Okay, so let's do some toy stuff to sort of make this point concrete. Say there are 5 products, and we're going to do some fiddling and see what happens to their relationships. As a prerequisite, primarily we need 2 things. We need the ability to tell, to measure the relationship between any given 2 products, and we need to decide, and we need to be able to decide if that relationship has changed. Those are those 2 things we need fundamentally. Here are some diagrams I made earlier to help explain what happens as a consequences of changes. And then hopefully at this point it should be obvious, well, okay, we can just look at these consequences as a marker of changes instead of trying to do the changes themselves. So no change, all of the relationships are nice and nothing, no change, relationships are stable. 1 product changes. Okay, 1 product has changed, and what happens? As a result, we have 4 changed relationships, and we have a whole bunch of other relationships that haven't changed. So the thing that has all of its relationships changed is the thing that has changed. And this develops in much the way you might expect. So here, 2 things have been changed, and as a result, all of their relationships have changed. And again, it makes it very easy to see which things have changed just by looking at the relationships, and which things haven't by just looking at the relationships, and so on. So we can't do the full 5 products, because by the time we get to 4, all relationships have changed. But in the real world, you're not working with 5 products, you're working with hundreds of products at the same time. Okay, let's do a spot of code. This is not a pipe. I'm going to switch screens, come back to my pipe not pipe later. Next thing to amuse and confuse you with will be the notebook. Slavik, are you still present, friend?
I'm always here for you. Yeah.
Thank you.
Here's your notebook.
Do you see my notebook?
I think everybody sees it now.
Lovely. Okay. Fine. Okay. So a notebook. Going to make some fake data to just illustrate the point. Slavik, how much time do I have?
We have been 18 minutes, so you have 7 minutes, 8 minutes.
All right. I'm on it. Right? Okay. Right. Okay. Here, I make a silly little class to make it easier to chain numbers together. And here I use that class to chain numbers together. When you've done all this chaining together, you get a diagram that looks like this. This diagram represents, say, for instance, what the trends in conversion rates might look like for 5 products. And it's been contrived in a very specific way. So reading it from left to right, here at 20, only 1 product changes and all the other ones don't change. And here at 30, 2 products change. And here at 40, 3 change. And here at 50, 4 change. So there's a bunch of changes that happens, and the idea is, okay, in this code, we're going to try and detect those changes, but without looking at what the individual series is doing. So we'll detect those changes purely by looking at the changes in the relationships. Here is the change detector, and I wrote this and commented it for your pleasure, mostly to just highlight what the kind of essential building blocks are. So we do 2 things essentially. So for every pair of products, we calculate at every time point whether there is a change in their relationship. And you might think of that as a sort of matrix that looks like a product times time tensor or array. That's what we do here in the fit function. And in the predict function, all we do is sum across one of the product dimensions. So we basically go from a product by time array where in the cells it's a Boolean indicating whether that product and that other product's relationship at that time has changed. We sum through one product, and that tells us for any given product at any given point in time how many of its relationships have changed. And that's the whole of it. So you have a silly bit of code like this, and you have something that does the actual relationship detection. So this data set is contrived of straight lines, so you can detect changes by just comparing gradients. But I'll talk about the real world in the next slide. So here's that resultant matrix. So here's the y-axis is the kind of index of the product, 0, 1, 2, 3, 4, and the x-axis is the time axis. And what you see here is how many changes were detected for each product. So if one thing changes, everything has at least one relationship that changes. So you see that sort of gray bar, but here we have only one that has all 4 changed. Here we have 2, here we have 3, and here we have all 4. So what we've done in this process is just use the relationships to find out where all of these changes happened for all of these products. So that's what we just did. You can review this in more detail in your own time. Now I have to hurry along and get back to my pipe. StreamYard, share screen. Hark, I think I want to go like 4 minutes. It's so stressful, Slavic. When is my paycheck coming?
We all are grateful to your effort. The community loves you.
Except Bitcoin. Okay, in a real implementation. Okay, this is a toy. This was a toy. But in a real implementation, there's lots of ways you might consider measuring relationships, starting with basic things like correlations. So you like sweep a window across 2 time series, and you calculate a correlation, and you can, for some use cases, use that as a measure of your relationship. So even though in the individual series themselves might be kind of fairly crazy looking and unpredictable, you might find that their relationships are actually not unpredictable, that they have a sort of stable aspect. Deciding whether these relationships change, this is another kind of matter, and there's lots of methods. Python has a great package called Ruptures that can help you, that just has a ton of methods in it that you could use. The third thing you'd have to do in reality is probably pick which relationships you actually want to include in your analysis. Probably not all products against all products. You want to pick products that there is a reason to believe have a relationship in the first place. And so far, I've really just discussed how to find the relationships. So a reason to believe that there's a causal relationship without experimentation, but I haven't discussed how you decide how big the change was as a result of a break in the relationships. But that is something that you have to do in reality. So I'll summarize at this point. So randomized controlled trials are the best thing in the world. You should do that if you can. But you've often got to do observational work in real life. The main problems when you have to end up being confounding effects, i.e. not being able to tell what caused what. Predictive models and synthetic controls are par for the course. That's what people tend to do. And if you've never done this before and just left you in the room, that's what you'd end up working out yourself. But sometimes it's easier to analyze the relationships between things than analyzing the thing itself. So hopefully that's something you can take away. And the toy example is the crux of it. It's much more complicated in reality, but it gets complicated by building on something simple. And this is the simple thing. And that's that. So just a final big thank you. That's my email address if you have comments, questions, or criticisms, whatever you like. And a final note, CGI Malmö is currently hiring for senior data scientists. It's a good place to work. So if that's of interest to you, please write me. That's it. Thank you, guys.
Thank you. Thanks a lot, Emir, for the exciting introduction. Actually, it's interesting. Basically, you replaced the say you study relationships between the products, not the, say, end results. Yeah.
That's it.
Anyway,
That's it.
we have a question from the audience. I popped it up here. So would this be considered in the realm of graph network data science? And do you know if I can do something like this with Neo4j?
Well, I mean, I suppose there's a question of like how to execute on it, and then there's a question of conceptually what you're trying to do. This isn't like inherently a graph database task. It's a sort of inference task, and the key bits to decide in reality are like how you'll measure relationships, how you'll decide if they'll change, and which relationships you're going to include in the first place. And then everything else is really about like the scale of your problem and what might be the best technical solution for you. So if you find that once you've done all that and you have a thing that you're trying to actually make, that you find yourself doing some sort of graph walks constantly in your solution, then Neo4j might be right. But more likely, it's just going to be a massive matrix, and you'll just need a way of doing linear algebra on a big scale. But it'll depend on what you end up making.
Okay, thank you. I have a question myself. I guess we have a couple of minutes. Could you give a simple live, like real life example for this relationship study from your practice? I don't know, would that be products or web pages or something?
Yeah, I can't say customers. I've been told. We've asked. I can't.
Okay.
But the customer has product pages.
Can you invent something for us?
Oh, so I can tell you the real thing. I just can't tell you who it is.
Okay.
Really, really, really big retailers. So they've got product pages. They add lots of content, and they simply don't know whether the content makes a difference. And they've been doing it for ages. So they know when they've added the content, but they don't know if the changes that have happened, and loads of changes happen, are in any way related to the content. So we use the historical data and we try and work out whether changes have happened and whether those dates match when they change the content or not.
Right.
So on one side, we use a method a bit like the one I've described to work out where the changes are. On the other side, we have dates of when they made changes, and we just look to see where the two overlap to decide whether their changes are causing changes or not.
I wonder if marketing efforts are useful or no, but maybe that's not a good question to ask.
Yes.
Okay, we have a couple more questions. But basically both relate. Both ask if you can share the notebook you just showed.
Yeah, absolutely. I didn't, but I should have. I've made a repo. How do I share it?
You can post it on Slack. So everybody who wants to see a notebook, we will post it on our Slack channel.
Yep, no problem. It's
We will
okay.
post the link.
If I post it in chat, will it do anything or not?
You can post it here, and I will copy it to the Slack channel. And I invite you to join our PyCon Sweden Slack channel as well. But you can post it here, and I will copy paste it.
Okie dokie. All right, I've just posted it to you. Hopefully you see that, and I'll just make it public now. GitHub has this thing now where you have to type like a whole sentence in order to change some settings. There we are. Okay, so that should be public. That link should work for all the people. Oh. Are there any other questions I can answer at the same time? Hello? Hello?
I'm sorry, my mic was muted.
Okay.
So there's a question about the Slack channel. Actually, the Slack channel is on our PyCon Sweden website, I guess.
Okay.
Or we wait, because the
So I was listening. So if you search for Emir Uz CGI and just find that account on GitHub, there's a repository there called PyCon 2021. And
okay, so those who want to join the Slack channel, please email to info@pycon.se. Okay, I think we have answered all the questions. Thank you again, Emir, for an excellent talk. I see there is a high interest to it, and I wish you all the best in hiring a senior data scientist at CGI.
thank you very much. Have a good day. Bye.